to Engineering Simple. In this video, I'll talk about power factor correction. So let me start with some kind of definitions or terminologies. So I'm going to use power factor I, which is basically initial power factor before correction, which is equal to cosine of the initial angle theta I. The power factor D, which is the desired or the final power factor, cosine theta D. So this is the initial power factor. This is what we want to correct the power factor to. And obviously the load will always be there. It's not going to change. If you have to serve the same load and you have to add a capacitor or some kind of reactive support equipment, the load should not change, unintentionally, unless it was going to change intentionally, which that's a different scenario. So this is the total real part of the complex power, which is typically fixed. But the reactive power, so PL, it kind of stands for load, QL kind of stands for load, so the reactive power of the load. So we're going to call LI, which is the initial reactive power of the load, which would be the real part or real power or active power times tan theta I. And I would recommend the previous video on power triangle. So basically, if you draw the triangle, so this is the real power, this is the reactive power. So this is theta I, which is the initial. This is the complex power, initial. So if you take tan of theta I is equal to QL divided by PL. So if you rearrange it, you can calculate QL is equal to PL times tan theta I. And you do the same thing for QLD, which is the desired, the reactive power. It's the reactive power we are trying to accomplish in order to correct the power factor, which is the desired QL. And also, if you do the power triangle, PL times tan of theta D. So then the required compensation or reactive compensation from a capacitor bank or a capacitor, if we're using a capacitor for correcting the power factor, would be, it's the difference in Q, which is delta Q is equal to QLI, the initial reactive power, minus the desired reactive power. And again, from the previous slide, this is equal to PL times tan theta I minus PL times tan theta D. You can factor out PL. That's tan theta I minus tan theta D. So that's the required reactive compensation in order to correct the power factor. So you see, all I did was basically just kind of draw the power triangle, and came up with this equation here and this equation here. And obviously, when you're trying to correct the power factor, you have reactive power and you're trying to reduce it by some amount. And we'll see how. So again, if you have, I'm just drawing a simple circuit for the sake of understanding this problem. So if you have a source and you have, this is load 1, then you have another load, load 2. So probably just for consistency, I'll write load 1 here. Then S supplied by the system is S1 from load 1 plus S2 from load 2. And what is S1? Is P1 plus J times Q1, right? That's S1 plus P2 plus J times Q2. So I just replaced S1 here and S2 here by their corresponding P's and Q's. And I can rearrange, put the real parts together, P1 plus P2 plus J times Q1 plus Q2. So we know the real part will not change typically, because the load has to be there and has to be served, you know. This is unless it's intentionally the load was growing, or that's a different scenario. I'm talking you have a load that you have to serve, but somehow the power factor is very low and you want to boost it or increase it, then that the active power will not change, but obviously this here will change. If you want to correct the power factor. So one scenario, if you have a lagging power factor, so for instance, so we can draw, like here's the total load, and again I'm going to use the power triangle. So here's the total load, and here's the initial reactive power, QLI. So here's the complex, the initial complex power. Obviously I want to make SI smaller, and also I want to reduce the reactive power. That's what I'm doing by the power factor correction. So this is the theta I, or the initial power factor angle. So in correcting power factor, I want to make Q smaller. So this is the desired reactive power, LD. And also, this is the power factor, or the desired power factor angle. So you see S became smaller, the desired complex power. So that compensation that I'm going to, or the capacitor bank that I'm going to add, that's the amount I need to add. So if you do trig and some geometry, so if you do geometry plus trig, you will arrive to the previous equation, which is the difference in reactive power that's required by the capacitor bank to correct the power factor, which is PL times 10 theta I, or the initial power factor angle, minus PL times 10 of theta D, which is the desired power factor angle. And also you do the same thing if you have a lead in power factor. So you have PL here, you have some initial reactive power, and here's the corresponding complex power, initial power. Obviously, you want to reduce this Q here to some value. That means you will reduce the complex power. So this is the desired reactive power. So here's the initial power factor angle. Here's the desired power factor angle. And this is the desired complex power. And obviously, this is the value that needs to be supplied by the device to correct the power factor. Another way of looking at this problem, you have load 1, and in this case I'm not going to assume leading or lagging. I'm just going to draw the power triangles. You have theta 1. This is in general. You have P1 here, you have Q1 here, and you have S1. Obviously you have load 2. So you have theta 2. You have the complex power 2. P2 is here. You have Q2 here. Obviously this has to equal to, sorry, the triangle was exaggerated. Again, I'm not assuming here lagging or leading, I'm just talking in general. So you have theta, which is the system angle or power factor angle. You have Q here, and you have P here, sorry, S. So, obviously Q is Q1 plus Q2, and P is P1 plus P2. And I showed that in previous slide. Now let's do an example. It's always helpful when you do an example. So we have a motor load which is served from a 2 MVA transformer, 2 MVA 12,470 grounded Y slash 480 delta volt, has an impedance of 6% and operates at 60 Hertz. So the load basically is 800 kilowatts with a power factor of 75% lagging. So you see in the FERP exam, you're going to have lots of information. Some of it is really for distraction. So you need to know which information to use and which one to just ignore. So you see there's impedance, so you shouldn't be fooled by lots of information. So, and we'll see how we can process the information to only keep what we need. So we would like to correct the power factor. So we would like to correct the power factor to 92%. lagging. And also get used to, you see power factor is given in percent instead of per unit, so it's the same thing. So now, question 1, what is the size of a lossless three-phase cap bank connected in delta to reach a power factor of 92% lagging? So that's question 1. So in order to correct the power factor from 75% to 90%, 92% lagging, what is the three-phase capacitor bank connected in delta that would establish this power factor? And we're assuming it's lossless, that way we don't have to deal with resistance. In theory, I mean, practically, there's no such thing as lossless capacitor bank, but the resistance is very, very small that you can ignore it. 2, what is the capacitance? So, and always when you are dealing with problems like this, the first thing you want to do is try to make a sketch, because a sketch will, and try to put information on it. That way, hopefully it starts making sense. So I'm just going to write a single line. So this is single line diagram. So I have a bus, which is 480 volt, and I have load, which is 800 kilowatt. Power factor is 75% lagging. So I need to connect a capacitor bank. It's a shunt capacitor bank. So what is Q and what is C? Reactive power and capacitance, or QC here. So that's single line. Now, if I want to draw a three-phase, obviously you have 3 lines because it's three-phase. And obviously this is line to line is 480 volt. So the load is connected three-phase. So I'm just going to call this load. So here's a load here. So I want to connect a capacitor bank in three-phase. In a delta form. So obviously delta, you have a capacitance here. So can connect that here. So I take this back because this is connected delta, so it's not grounded. But anyway, so I'm trying to calculate the capacitance and also the reactive power of the capacitor bank that would establish this power factor. So as you can see here, this is, you can call this S1, this is S2. Obviously S1 or S2 will be P2 plus J times Q2. In S1, there is no, I'll write in the next slide. So the total S, or complex power, is S1 plus S2 P1 plus J times Q1 plus S2 is P2 plus J times Q2. So S1 in my case is the capacitor bank. So since I said it's lossless, so it's 0, and it will be negative because capacitor banks supply reactive power minus J Q1 which I can call C, referring to capacitor, plus P2 plus JQ2. So now P total is basically just P2, which is 800 kilowatts. Actually, I can rewrite this as P2 plus, because P2 plus 0 is just P2 plus J times Q2 minus QC. So again, using the power triangle, so for the motor load, P is 800 kilowatts. I know the power factor is 70, so the power factor is, let's see, is 75% lagging. That means so I call this P2. So power factor of 2, theta 2 is the inverse cosine of 0.75, which is so 41.41 degrees. So Q2 I can calculate, because I know this is 41.41 degrees. So I know 10 of 41.41 degrees equal to Q2 divided by P2. So Q2 is equal to 705.53 kVAR. And what I'm trying to do is, so obviously I have theta 2, P2, Q2 here, and since capacitor bank will have a negative reactive power, that's QC, so this plus this basically would equal, you have total active power of 800 kilowatt, Q2, the initial Q2 is here, which is 705.53 kVAR. This is S2. So this is theta 2, which is 41.41 degrees. So I want to reduce that Q to some value here, to some desired Q. That means the capacitor, this is the amount the capacitor will provide, And what is the total power factor that I'm trying to reach is 92%. That means the inverse cosine theta is equal to 23. No, sorry. That means the inverse cosine of 0.92 is equal to the angle theta, which is, if you carry that out, 23.07 degrees. So that's really the angle that I'm trying, that's the desired power factor angle. And previously we said delta Q is the total load times the initial power factor angle minus the total load, reactive load, times the tan of the power factor angle of the desired angle. So P, and also this you can factor out PL desired. So PL is just 800 kilowatt times, so times the tan of theta initial, which is the inverse cosine of 0.75, which I calculated to be 41.41 degrees, minus the tan of the desired power factor angle, which is 92% power factor, which is the angle is the inverse cosine, which I calculated here, of 0.92, which is 23.07 degrees. So if you calculate that, you will get 364.74 kVAR. So that is the required, the reactive power that the capacitor bank needs to provide. Obviously, you have to keep in mind capacitors supply negative reactive power. That means the size of the capacitor bank will be QC equal to minus 364.74 kilovar. You don't have to put the negative sign as long as you remember that the capacitor bank supplies reactive power. That's what really the significance of the negative sign. Negative sign, it just means that the capacitor bank will supply that reactive power. Really, that's what it means. One thing, like when you correct the power factor, so note that with power factor equal to 75%, the current, the total current that will flow is equal to complex power magnitude divided by square root of 3 times the line to line voltage, which is 100 volts. So 800 kilowatt divided by 0.75 divided by square root of 3 times 480 volts. So the current is equal to 1283 amps. So that's the current. With the power factor of 92%, the current is equal to, it's 800 kilowatt divided by 0.92 square root of 3 times the voltage, which is line-to-line voltage, which is 480 volts, which is equal to 1046 amps. So you see the total current was reduced by correcting the power factor, was reduced from 1283 to 1046 amps. That's one observation. So the reduction so you see the current was reduced by about 18.47%. So 2, we want to calculate the capacitance. We know QC is equal to V squared divided by the impedance of the capacitance. And note, the capacitance, the impedance of the capacitor is minus J times reactance, which is minus J times 1 over 2 pi F times C. That means, so if you rearrange, if you rearrange, you will get C is equal to QC, the reactive power of the capacitor that I calculated, 364.74 kilovar, divided by 2 pi times the frequency times the voltage, line-to-line voltage squared. Obviously, if the reactive power of the capacitor is 3-phase, then voltage will be line-to-line. If it's single-phase, then the voltage will be line-to-neutral. Or per phase voltage. So you have to keep that in mind. So I'm going to use 3-phase. So I calculated 364.74 kVAR divided by 2 pi. System is 60 hertz times 480 volts squared. So you get 4.2 millifarads. That is the capacitance of this capacitor. So the reactive power that the capacitor bank would correct the power factor from 75% to 92% is 364.74 kilovar, and the capacitance is 4.2 millifarads. That's it for this video. Thank you and have a great day.